Well, welcome everyone. Thank you so much for coming tonight to our fall educational program here at the Superior Community Center. And we've got a very nice crowd. This is going to be an interesting presentation, I'm sure. My name is Larry Dorsey. I'm the chair of this Superior Historical Commission. And we have a few other members in the audience tonight for crowd control, rowdy crowds. So, Karen Waldorsky, say hi, Karen. And Scott Phillips, Mary Cartwright, and let's see who else, and Maureen Hogue. Thank you, everybody. So those are the members of the Historical Commission who are here this evening. And so if you have any other questions after the program, pick out one of us and we'll give you an answer, hopefully be the answer to your question too. That's always helpful. Well, this evening, let's see, I think that's not all I need to cover. I'm going to introduce you to Maureen Hogue, and it's her idea to come up with this presentation regarding the geology of this area here along the Cold Creek Valley. And so I'll have Maureen introduce our speaker, and we'll go from there. Thank you again.
Thank you, Larry. I'd also like to thank my fellow members of the Superior Historical Commission. It's a team effort to preserve and promote the history of Superior. Thank you, Leslie Clark, and all the town staff who support the commission. In particular, the Board of Trustees should be recognized for its proactive attitude in preserving the historic programs. It's the more remarkable in the wake of the Marshall Fire, which is historic in itself. As some of you might know, I'm a freelance writer based in Louisville, but I sit on the Historical Commission as a family tradition. I'm a direct descendant of William and Emmeline Hague, who first settled in the Cold Creek Valley in the spring of 1860. They were the first owners of the industrial mine and a part of the founding of Superior. They named the town in honor of the quality of the coal mine here. Now that raises the question, what made the coal superior to the other coal mine in Colorado's Northern Field? Tonight I'm pleased to introduce you to Jeff Graves. He's program director of the Division of Reclamation, Mining and Safety in the Colorado Department of Natural Resources. He's the go-to guy for the nitty-gritty on coal and how it shaped the history throughout Colorado. I hope you'll enjoy our presentation tonight. Over to you, Jeff.
Thanks for the kind introduction, Maureen. Appreciate it. And hopefully I can live up to the go-to guy for geology and coal in Colorado. And I'll do my best to answer the question, whether it's really a question anymore or not, as to why is Superior's coal superior. So we'll get to that at some point through the presentation. And I'll kind of point to things on the screen. I may walk over there a few different times as we go through the presentation because there's some areas I want to focus on and I don't have my pointer with me, so I'll try and move around a little bit. But here's just an overview of the presentation I'm going to give tonight, so you have kind of an idea. So I'll give a quick introduction. Maureen did most of that for me, so we'll go pretty quickly through that. We'll talk, obviously, about the geology of coal in Colorado and kind of specifically focus on the Front Range, some characteristics of that coal. Touch on mining methods, just so you have an understanding of kind of modern mining, some of the historic mining methods that were used, because that does influence a lot of what we see on the surface nowadays with respect to how things were mined in the past. And then we'll kind of focus in specifically on kind of the Boulder County area and Superior specifically. And then I'll kind of break things up and talk a little bit about the program that I manage within the Division of Reclamation, Mining, and Safety, because we deal with a lot of the modern day problems associated with that historic mining activity in Colorado. So I'll talk about kind of our program a little bit, and then talk about some specific projects that may be of interest to you folks here in Superior. We're doing some mine subsidence work up in Lafayette, and then over in Frederick, I think it is. And then also talk probably more specifically about something that's very close to you guys with the Lewis Mine Fire project that we're working on or completed early this year. And then also the Marshall Mine coal fire project that we're going to be starting in a couple of weeks. So that's kind of an overview of what we're talking about. Feel free, I'm pretty open to questions throughout this. So if you have a question, I don't mind if you raise your hand or just blurt it out. So I don't mind it if it's interactive through the presentation here. So just so you have kind of an idea, the program I manage, where we sit kind of within the structure of the state. So we are within the Department of Natural Resources, and then within the Division of Reclamation, Mining, and Safety. And so my program that I manage is the inactive mine reclamation program, sometimes referred to as the abandoned mine program. Within our division, we also have a mine safety program that trains miners in different skill sets at mines. And then we also have our active mines department that regulates coal mining in the state. There's still a few places that we mine coal in the state. We have 5 active mines right now. And then also our minerals program, which pretty much manages all other mining outside of coal, mostly aggregate construction materials, but also gold, molybdenum, and silver. So it's kind of an overview of where I sit within the structure. And so we're here to talk about coal tonight. So what is coal? Well, there's the formal definition of coal. Essentially, it's just organic material that's been turned into rock over time. The pictures I have up here on the slide are pretty much where modern day coal is being made as we speak. So coal really has its origins in swampy areas where you've got lots of plant material that accumulates over time. Or the lower right photo over here, that's a wetland. So in areas where you've got large wetlands that stay wet for extended periods of time, that's where coal is currently being made. So as a geologist, we're always looking for analogs for things we see in the rock. So we're looking for where is what we see in the rock being constructed or made in modern day times so that we can have an understanding of how things occurred. So when you go digging into the rock, you know what to expect. So those are good kind of idea of where coal was generated. So when we talk about coal, there's different kinds of coal. Really, there's the kind of beginnings of coal, and that would be peat. And so in that upper left photo, you see how the coal over time and pressure becomes lignite, which is mined quite a bit up in North Dakota. Some lignite here in Colorado. With more pressure and heat as it's buried more deeply, it turns into subbituminous. That's actually what most of the coal here is within the Denver Basin and within Colorado. And then you get higher grades of coal as you have deeper burial and more heat that influences the process of generating that coal. And then kind of that chart down here on the right is a lot of information, but really the coal ranks, so there's lots of different coal ranks. But the key to remember is kind of the coal ranks are based on BTU, how much energy that coal can produce when it's actually burned. And so the lignite, lowest BTUs, and you move up into bituminous, where you're getting about 14,000 BTUs, and then into anthracite, which is really highly compressed coal, lots of heat, lots of pressure, and you fixed all that carbon in that material, so it's really good coal. Most of the time, anthracite is used for coking coal in terms of making steel, so it burns really hot. Surprisingly, there's one location in Colorado where we actually have anthracite coal. It's actually in the Crested Butte area. There's a small anthracite district. Otherwise, most of the anthracite is mined back east in Pennsylvania. So for the context of our talk today, pretty much talking about subbituminous coal, roughly in that 8,000 to kind of 10,000 BTU range. So, Colorado coal fields. I mean, we're specifically talking about the Denver region today, but as you can see, there's coal fields pretty much all along the western side of Colorado, up into North Park, and then a coal district down in Raton, so kind of Trinidad area, Walsenburg, it's kind of that Raton coal field. Interestingly, I was looking at production, historic production kind of throughout the state for the different coal regions. The Denver region or Denver Basin, I think, accounted for about 12% of total coal production in Colorado. So not significant. In Colorado, I think there's been about 1.2 billion tons of coal mined historically. Pretty big number. So about 12% of that was Denver Basin, and that ranks 5th in terms of all the different coal regions in Colorado. The majority of the coal has kind of come out of the Uinta region. So that's Garfield County, so that would be Glenwood Springs area to the west along what's called the Grand Hogback, up into Moffett County, and that's actually where the bigger modern mines are, and you've got much thicker coal seams. So that's the #1 producing region in Colorado historically, and actually currently. So another complicated slide. What I wanted to highlight in the slide here, these are geologic columns from the different areas within those coal fields, and you can kind of see the coal lines up age-wise, all about the same, kind of through the middle here. That's about 70-ish million years ago, kind of towards the end of the Cretaceous period. So it's, I got a slide here in a minute that kind of shows why that is, but for the vast majority of coal, it's all roughly the same formations throughout Colorado. There's a little bit of coal in a much younger formation here in the Front Range called the Denver Arapahoe Formation. You may be familiar with that from the Denver Arapahoe Aquifer, which is a big aquifer within the Front Range. But there's some much more recent coal that's lignite coal in that formation. But the majority of the subbituminous coal, the good coal that was mined kind of around here, that's all in what's called the Laramie Formation, which was kind of towards the end of the Cretaceous period. Okay, so the picture on the left is a picture of the Western Interior Seaways. That's a historic reconstruction of what things would have looked like here in Colorado. And Colorado, really hard to see, would be right about here. So what happened with that Western Interior Seaway is it advanced and then regressed. It kind of came in, went out. When it came in, you had lots of basement sediments that were deposited. That would be the pure shale that's kind of out through, it's kind of the western side of Lakewood, kind of along through there. It's a big section of essentially sea sediments that were deposited. As that seaway dried up and moved towards the north, you had a lot of channels that would form coming off the mountain range, and swamps that would form, much like you see down in the Gulf of Mexico along the Mississippi Delta, and you've got all those rivers moving into the Gulf. That's similar to what was happening in Colorado as that sea regressed. And so you had these big swampy areas along the edge of that interior seaway. As the seaway went out, those swamps developed and kind of moved up towards the north. And so you've got that coal seam that forms during that period of time in which you had regression of the seaway. And so that's kind of what you see here is this coal formation where you'll get channels of like the Mississippi Delta moving into the seaway, and you've got swamps surrounding that. And you'll have those levees that are built up naturally along those channels, and they'll break out. And that's where you get these little sandstone lenses in your coals, all that kind of stuff. So this is kind of the formational equivalent of what you see, how things are occurring in modern day times and what would have developed historic coal. But it's really a function of that western interior seaway that advanced and then regressed over time. Just kind of another picture of what happens with coal formation. So we'll do another nice geologic map here of the Denver Basin. So we'll kind of focus in on the Denver Basin, and that Denver Basin is really just an accumulation of sedimentary rock from the hogback on the west out towards Kansas pretty much. It's deepest over towards Denver, kind of along the Front Range where it dips down, and then it slowly gets more shallow as you move to the east out towards Kansas. And so you've got the Golden Fault down here towards Golden that created that uplift and then overturned some of those beds. That's what you see, the hogback over there along the Front Range. That coal directly adjacent to the the hogback is vertical in most places. Around Golden, over in Lakewood, most of the coal was vertical at that point. Up here in Boulder, kind of Boulder County, once you advance past, I think it's about 58, just north of Golden there, you lose the Golden Fault, and that coal actually becomes more flatline as you get to the north, and then continues kind of flatlining out into Erie, Frederick, Tacoma, that area. So it's kind of a different mining situation, but really you've got this Laramie Formation that crops out towards the west, and then gets deeper and then gets shallower towards the east. And so this is looking cross-section with the blue line there. Here's Denver down here. And then that blue line is this cross-section. And then if you were to look north-south along the basin, it's kind of deepest right around Denver, down here in the south. And then you actually have this similar coal basin up into Wyoming. So you kind of got a ridge. So, but that's where all that sediment accumulated over time, got very compressed, and really turned into that coal.
Could I ask what time period we're talking about? I mean, you say over time, what, 10 years, 100,000 years? How long?
Millions.
Okay, all right, that's fine, that's
Sure.
fine.
Yeah, orders of magnitude, we're definitely talking about millions of years. So most of these formations, the Fox Sandstone, which is the kind of the lowest formation here in the Denver Basin, that's 75, 80 million years old. Like I said, the coal's about 70, and then you advance up into I think the Castle Rock Formation, Castle Rock Conglomerate, and Dawson Sandstone are the youngest, and those are, I think, in the 40 to 30 million range. And then you've got kind of sediment, non-compressed sedimentary rocks, alluvial rocks on top of that. Another good geologic cross-section, so all this yellow cross-sections. So this is a cross-section within the Denver Basin. So this would be equivalent to kind of the coal section you're seeing here in Superior, even down towards Marshall, up towards Erie, Frederick, all that. It's a very similar section. You've got 7 different coal seams within that kind of Laramie section through there, kind of numbered from 1 at the bottom all the way to 7 at the top. Nothing unique. When you're actually trying to drill through and identify those beds, it's really difficult. We've done some drilling down in the Marshall area, and it's really hard to discern what coal bed you're in. Unless you drill all the way down to that bottom sandstone member, this big yellow here, or the Pierce Shale, you can't really tell where you are in that section. But needless to say, there's a number of different coal kind of sequences within that Laramie Formation. And that's a function of that seaway kind of advancing, moving back. And so when it advanced out, those swamps would form. When it come back in, you'd have sediments precipitating that weren't plant material. So it's just a function of that seaway changing its location that dictated some of those coal beds. And then also on that previous slide, we had these levees that develop adjacent to your rivers. When those would break, it would wash sand out over some of those kind of marshy areas, and that's where you get some of those sandstone lenses within that sequence. The main sequences that they mine, just based on thickness, where I believe the coal bed number 3 and 4, those are about 4 to kind of 15 feet in thickness, and it varies depending on where you are within the coal seam. Coal bed number 1 is pretty narrow. It's like a 1 to 3 foot thick seam, and then some of these upper seams, they didn't get over about 8 to 10 feet. So most of it was kind of those middle coal seams, and coal seam 2 and 3, and then some and 4. Okay, the question. Is superior coal superior? Hopefully I'll answer some of that. So here's just some comparisons of different characteristics of the coal. These are like moisture content, volatile matter, fixed carbon. So that fixed carbon component is the longer it's buried, the more it's compressed, that carbon gets fixed, and so it's easier to burn. So compared to the other regions in Colorado, the coal in the Denver Basin is not necessarily the best. Sorry. Just in terms of comparing other areas, that's really because those areas had deeper burial and more heat associated with the generation of that coal. Here's some more numbers down here, BTU values. When you start to look within the Denver Basin itself, the area here in Boulder, what we call the Boulder Weld Field, does actually have higher BTU values than the other areas within the Denver Basin. And so I'll show that on the next slide. So within the Denver Basin, yes, Superior coal is superior. Compared to other regions of Colorado, I would say it's a stretch. But definitely within the Denver Basin, you'll see these are actually BTU values from around the area within the Denver Basin, and that 9,700 BTUs is the highest. So it ranges anywhere from, let's see, about 6,000 BTUs over towards Lyman up to that 9,700 here in the Boulder, kind of southwestern portion of the Boulder field. So there's the answer to your question. Superior in the Denver Basin. So we'll talk a little bit about how coal was mined. So this is kind of a good schematic that shows different mining methods. The mining methods on the right are what we would consider surface coal mining methods. Here in Colorado, there was some surface mining of coal historically, but most of that surface mining is more modern day. When you get up into the Colorado mine, which is just south of Craig, kind of south and west of Craig, that's a big open pit mine where they're using big dragline pieces of equipment like you've got down here, where you're mining a much thicker sequence of coal. Up there, I think they've got some 50 to 60 foot big sequences of coal. Really thick, it's really conducive to dragline mining. Just some other different mining methods. Mountaintop, we don't really have mountaintop removal in Colorado. That's kind of an eastern thing. But the thing we do have quite a bit in Colorado, and really what took place for the most part here in the Boulder field, was underground mining through shaft mines. So coming up, most of the mines kind of within the Boulder field had shaft access, and so it was all underground mining. Some of them had sloped entries. You can kind of see this picture here where you've got a slope entry coming into that coal seam. So there's a number of slope entries, but then you also get quite a bit of shaft mining that took place. And on the next slide, I'll kind of show the different underground mining methods, because this doesn't do a real good job of depicting that. So these are modern underground mining methods. I'll say the picture on the left is the mining method that was mostly used historically here in the Boulder field, just not with that modern equipment. So it looks a little bit different. But room and pillar mining is pretty much what took place within the Boulder Weld field. Pretty much all along the Front Range here was room and pillar mining. And so essentially they would go in, create entries or mains they would drive down, and then they begin to develop what's called a panel off to the side of those main entries. And they would leave pillars in place to support that overburden material. And so they mine out the coal and then leave a sufficiently sized pillar, hopefully, to support that overburden material. Another method that they would often use towards the end of mining is they come in and rob those pillars, called pillar robbing. And so they come in and mine out those pillars and then allow the mine to collapse. Obviously, that's a very dangerous type of mining, because you're not exactly sure at what point that overburden material is going to fail. So you're just removing that coal, trying to get every last bit of it out of there. So I've kind of got a picture where that's naturally occurred in the next slide. The other method is longwall mining. This is used quite a bit back east. Also over in West Elk near Paonia. That's modern day mining. They're using longwalls. It's essentially you've got a big shearing wheel that runs across that coal face. It removes all the coal. Behind that shearing wheel that runs across the coal face, you've got big hydraulic supports that support the roof in place, and that shear just kind of advances. And those hydraulic supports support the roof, and then when it advances, it allows it to collapse behind it. So you're essentially collapsing as you mine. It's an interesting mining method. But none of that was used out here in the Boulder field. Everything was pretty much room and pillar mining. And that room and pillar mining is very evident on surface when it's had collapsing associated with it. This is a picture. Does anybody know where this is? I'm sure somebody knows.
Superior.
Marshall, yes. So here's the Davidson dish, right? And then Cherryvale and Marshall Road would be down here in the left corner. So this is the Lewis mine. And you can really see this pattern kind of developed on surface, all these linear kind of features you're seeing through here. That's those collapses in between. So that's the room collapse, and then what's kind of remaining high is where that pillar was. So that's that kind of formation. And so you can see here they're pretty narrow rooms and then pillars, but that's what tends to develop on the surface in room and pillar mining once it's had time to fully collapse. So this one's pretty close to the surface here. I think we're talking about 40 feet maybe. Some spots a little bit shallower. Okay, so Boulder Well Field. Boy, you can see here, this is up towards Frederick, Dacono, Erie, all the way down to Marshall's kind of the lower left over there. So you can see that Boulder Well Field goes all the way across Boulder County up into Weld County. The coloration on the map indicates the depth of mining. And so the darker color, I can't read it, it'll be on the next one. I've got a zoomed in picture of that area. But I wanted to put this one out there just so you can see the extent that was mined. So everything that's colored there was mined underground. Pretty extensive. Hundreds and hundreds of acres. So here's kind of a zoomed in picture of that red area. Here's the industrial mine right down here. Here's 36 in the Caslin. Up here, Marshall Lake, and so that's Marshall down over there. To kind of get an idea, the colors here, the yellow is 0 to 50 foot depth. So that's really shallow mining. That's most of that area over towards Marshall. You get down here to the more indigo color, and that's over 400 foot depth. And so you've got a pretty big transition between 50 foot to 400 feet in a lot of these coal areas. What's interesting in the Boulder Well Field is you've got a lot of, all these black lines are faulting. So that's really what separates a lot of these mines and why they're not quite actually as extensive as they could be. So what happened is you had expansion in these sediments, and as those sediments either compressed or expanded, it created faulting that moved those layers vertically. And it's called Horst and Graben is the technical term for it, but you get these big kind of ridges and basins. You don't really see that now because it's all been eroded down, but that's what you have under the surface. And so they would be mining in one of these coal seams off of the shaft towards the northwest, and then they would hit this fault and there'd be no more coal. And who knows if it went up, if it went down. Occasionally they would drag what's called a rock tunnel. If they had some idea where the coal, which direction the coal was displaced, they might drive a rock tunnel to access it, and it might be up, it might be down, but for the most part, when they hit those faults, they quit mining. And so that's when you see a very distinct kind of break on a lot of those mines is because of those vertical faults that displaced the coal. And it either was completely removed because it was eroded off, it got raised, and where they were mining was lowered, or vice versa. I did kind of highlight the Pluto mines right here. So this is 36 again. That Pluto kind of extends up across or underneath 36. And then the Gora mine I think we were talking about earlier. That's just down to the kind of south and west of the Pluto. And then obviously the industrial here, just kind of on the south side of Superior. Extensive mine. That was a very good mine, the industrial.
Excuse me, I have a question.
Sure.
Approximately what year did the mining, or around when did it start and when did it end in this area?
That Maureen has the exact answer. So I think most of this was early 1900s, kind of right around the turn of the century, and I think they mined up until about the 40s, and some of these maybe the 50s. I don't know.
1943, the industrial closed.
There you go. So that was
Thank
close.
you.
40s. 40s or so.
Did it close because there was no more coal or because of the economics?
Economics.
Economics.
Probably. What you end up with as all of that shallower coal's developed, it becomes much more expensive and difficult to mine that deeper coal. And so you kind of run out of area that is economically accessible. And shaft mining is expensive. Because not only do you have to hoist material up and down, which is costly, you've also got to deep water. So most of these mines would have been below the water table, so you have to pump water out, which is very expensive. And so it's a lot easier to get coal from areas where you can surface mine it and you don't have to deal with the underground. And so that's really where you have the development of that Uinta Basin in northwestern Colorado. Much thicker coal sequences, all accessible from the surface, much easier to mine, much less expensive to mine, and you've got rail access to. So. This one's hard to see unless you're up here close, but this is the historic aerial. We have a bunch of these maps back at the office where we maintain our Mine Subsidence Information Center. But these are actual overlays of the mine workings. So we have mine workings maps. So 36 in McCaslin, obviously many years ago. But you can see kind of the extent of where the industrial is. And then over here towards the Pluto, you can actually see some of those mains, which are more of a tight checkerboard pattern where they were doing haulage. So it's a haulage main. And then off to the sides of those is where they developed their rooms and actually mined the majority of the coal out. And this is just a good way to kind of see what was going on underneath, where those rooms were, where the mains were. A lot of times you'll see where the mains were, they left most of those pillars in place because that was their haulage route. They couldn't afford to have collapse along those. Those are the areas that are best supported. Anything that was either mined out or was in one of those panels that they remove coal from, that's usually where you start to see subsidence occur first. Those mains tend to be pretty well protected because they left large pillars in place for the most part. So that's a lot of times what we use those maps for is kind of to predict mine subsidence risk associated with how those mines are laid out, where you're going to see subsidence, that kind of thing. And so here's just hard to see on here, but this is a picture of the industrial. And in this photo, it kind of overlays where the industrial mine workings are and the depth to the mine at those locations. And that's what those contour lines reflect is like 300 foot, 350, 400 foot, 450 foot below the surface. So we'll kind of transition into more modern day stuff. I'll talk a little bit about our program. So that's kind of the geology as a whole. It's a good snapshot of what's going on with respect to the geology, how it was mined, where it was mined, kind of big picture of the coal field. How does that influence modern day? I mean, obviously we're not mining anymore out here. So what are those impacts that we have to deal with as a result of that historic mining? And so that's where our program comes into play. So we're the inactive mine reclamation program, AML for abandoned mine lands. So these are just sites that are historic or legacy mines in Colorado. We kind of have a cutoff in my program where anything that was mined prior to 1977, we consider legacy mining. And the reason for that is that's really before any reclamation laws came into effect. So prior to 1977, if you were mining coal, you did not have to have a permit or a reclamation plan or a bond or anything like that. So post 1977, all that was required. And so there's always a responsible party for that going forward. So we don't have to do anything. Theoretically, there's a responsible party. So the kind of work we do coal fire investigation and mitigation. I'll talk a little bit about some of those projects. We do coal mine subsidence abatement. We've done quite a bit up in the Boulder Well field, also in Colorado Springs. I'll talk about a couple of projects we have going on. Another thing we do is we do safety closure work. So for those that do venture into the mountains, you've probably seen mine waste piles all over the place, in orange, on the hillside. So we do safety closures on those portals or entries. We construct graded closures or backfills to keep people out in mining regions. We do some water quality related work, and then our program does bond forfeiture work. So on mine sites where the operator walks away and leaves the state holding the bag for cleanup, they have to post a bond, and so that bond we use to then do the reclamation work. So Colorado's mining legacy. So this is a little bit of kind of our history. So our program began in 1980. We did an inventory across Colorado at that time and visited 8,000 mine hazards that were inventoried across the state. Obviously, that's not even scratching the surface on how many actual sites there are. We estimated about 23,000 as a result of that, but based on our work since then, it's probably more like 50 to 100,000 sites throughout the state. So significantly more than we even inventoried. We have about 33 active underground coal mine fires. I think we're actually up to about 40 right now. It kind of varies depending on whether something's kind of in dormancy or not, but there's quite a few in Colorado. Most of those are on the west slope. I'll show a photo of kind of depicts where those are. And then you've probably seen, I mean, like Gold King related orange streams, that kind of thing. In Colorado, you have about 400 sites that impact water quality, so there's 1,300 stream miles that are impacted by acid mine drainage coming from sites. Most of that's not coal related, it's hard rock, but that's something else we work on. And then there's been about 20 deaths attributed to AML hazards. Just photos of different types of mine features. We do work on uranium related projects on the west slope, in the Natarita area, and then we have a number of neighborhoods in Colorado that have been undermined. Most of Lafayette, areas of Louisville, obviously some areas here in Superior. Move into Erie, Frederick, Tacoma, Marshall. I mean, all of these areas have undermining. There's significant undermining in Colorado Springs, Rock Rimmon neighborhood, Colorado Springs, country called Circle in Colorado Springs. So a lot of these areas that have had communities built on top of them have historic underground mining that most people don't even know about actually is there. So, and then we do coal fire work. So here's where our coal fires are and spread throughout the state. You'll see we have our Marshall number 1 and 2 and the Lewis 1 and 2. It's really the only area here in the Front Range that we have active coal mine fires. Most of them are located on the west slope, kind of really concentrated along what's called the Grand Hogback, which is a geologic feature just to the west of Glenwood Springs, where those sedimentary beds have been uplifted due to faulting and folding, and it creates a situation where if you do get a fire burning in one of these mine sites, it creates a chimney effect because of the way the coal was mined on a vertical section like that. They went in down low, removed the coal, and then mined upward, and so you get a natural chimney once that coal's been removed. And they never removed all the coal, so you've got really intense fires kind of along that section, and much bigger coal seams. So it's really where we have most of our really active coal mines in the state and focus our work on. And then we have AML hazards, just water quality stuff, and that is Gold King on the right there. So always interested. So different things that we do. Our program does a lot of investigation work, but we also do contracting. So we do design work, and then we hire contractors to do AML reclamation, and that's what I'll show here in a minute on the coal fire work that we're doing. So we hire contractors to do that kind of work. But we do a lot of design in-house. We do some historical preservation on sites, working with local historical societies to shore up structures that are unique and have significant value to that community. So we do a kind of a varied bunch of work. I have geologists, rangeland scientists, some engineers, biologists, I have an archaeologist that works for me. So we've got a pretty broad set of expertise within our program. Program funding, probably not a lot of this will mean a whole lot to you, but our program receives about $15 million annually to work on all AML hazards. So that's not just coal, that's hard rock or non-coal related work. The IIJA, BIL, the Infrastructure Investment and Jobs Act really funded our program substantially. We started receiving that in 2021, and that's $10 million annually for the next 15 years. So that's what we're actually using to fund the work over in Marshall and Lewis that I'll be showing here, and then some of the other subsidies work we're doing. So we're able to really kind of supercharge our work on some of these coal fires that may not have been, not that they weren't a priority in the past, but we were having to focus on things that were a higher priority based on our limited funding. So that really gave us an opportunity to do some significant work. And so our program over 44 years, we've safeguarded about 13,500 hazardous mine features, and we do about 300 of those a year through contracting. We have quite a few in Boulder County, up towards Jamestown. 2 projects going on right there right now. Reclaimed over 4,100 acres and done environmental reclamation on 220 sites. It's quite a bit of work. So we'll talk projects. So coal mine subsidence, I mentioned that there's a lot of communities in Colorado that are constructed over historic abandoned coal mines. So let's see. This is Simpson Drive in Lafayette. This is Simpson Drive in Lafayette, another shaft that collapsed. That one I believe is over in Erie that the Subaru fell into. It's another shaft. And then this is down in Colorado Springs near Templeton Gap. So happens all, I'm gonna say all over the place, but we get one of these maybe every couple of years. Most of the time, these kind of collapses are a result of generally a shaft that may or may not have been identified in the past. And that shaft will collapse and swallow pretty much anything at the surface. And that's what certainly the three on the left or the one on the right is more descriptive of the subsidence, but it's not unusual. Just kind of some schematics of what happens when you've got coal mine collapse following removal of coal. So you kind of have two different scenarios where you get what's called trough subsidence, where you've got an area of coal that was removed and then that overburden material collapses into that area, kind of breaks the sedimentary layers. It does what's called bulking, as it breaks up, it takes up more volume. And so that's why I kind of mentioned in areas that are like 400 to 450 feet deep, you don't get a lot of expression of that subsidence at the surface because that material bulks up over time, so you don't get big subsidence events at the surface. In areas where you've got limited amount of cover over the coal mine, that's where you get the most expression of subsidence at the surface. But trough subsidence happens a little bit, but mostly over more shallow areas of coal. What we see more of kind of in the Boulder Weld field are these shafts that collapse. So a lot of times what you'll have is when they're done mining, they just start throwing things in the hole. So they'll throw trash. A lot of times you'll end up with rail that'll get wedged into the upper areas of those shafts. That accumulates debris on top of it, and so it looks like it's solid surface. And so people pave roads over it, whatever. Over time, that groundwater, as it goes up and down, it starts to erode at the bottom of that collapsed debris. And then a lot of times you'll have kind of that catastrophic collapse effect. And so we tend to see, for the most part, chimney subsidence, shaft subsidence in the Boulder Weld field, not as much of that trough subsidence influence. Most of the time you can associate those chimney subsidences back to some kind of a shaft located on those mind maps, which is why I mentioned we love having those mind maps, because we can come back to geo-reference. So we can come back and say, oh, that looks like it's the Simpson air hoist shaft, as depicted on the mind map. And so that gives us a pretty good idea on depth and what to expect. So one of the projects that we're going to be starting on this year is up in Weld County in the town of Firestone. It's Firestone shaft associated with the Firestone mine. So here's a picture of those mine workings. So this is that main that I was talking about, those haulage ways. These are the panels where they remove most of the coal. We got reports of some surface subsidence kind of in that area. When we went back and started looking at the maps, we were able to identify what we think are some collapsed shafts based on the maps in that area. So what we end up doing once we've identified one of those shafts to stabilize it is we do drilling and grouting. So we'll actually go in there and it's kind of an example of a drill rig on the side. So we'll set up either adjacent to that shaft or on top of it. Drill all the way to the bottom of that shaft. Firestone shaft's about 150 feet deep. So we'll drill all the way to the bottom of that shaft, and then we pump a very thick concrete or grout mix into that. And that takes up the void space, if there's any void space, and then you pump to a certain pressure. And so at depth, we'll pump to 600 PSI. And so as that grout bubble expands, it compacts any of that material around there. So you end up with a column of concrete in that shaft. So that keeps that shaft from collapsing into the future. We still recommend that you not build on top of it, but at least we're not worried about some kind of catastrophic collapse event that might swallow someone's home or a road or some other type of infrastructure. But essentially you're just pumping grout, you pump it, start at the bottom, pump to a certain pressure, you pull up a foot, and you just kind of do this progressive, it's called upstage grouting, pumping grout in there, taking up that space all the way to the top. So, pretty simple, not cheap. So another one is we're going to be working on the Simpson air shaft. So I think I had kind of a different angle of this picture on the first slide, but this is on 802 Simpson Street, downtown Lafayette. This is the Simpson Mine air shaft. About 8 years ago, the Simpson hoist shaft collapsed in the street one block over. And so we did an emergency mitigation where we came in and poured concrete on top of that collapse. And then we came back after that, drilled to the bottom of the shaft, pumped it full of grout all the way to the surface. This one, we've already done that kind of emergency surface mitigation where we came in and poured some concrete, put some rock in the hole just to stabilize the surface. And then we like to come back and do that more thorough kind of grouting job after the fact. And so that's what we'll be doing this year at the Simpson shaft, drilling down through that, pumping grout all the way to completely remove any risk associated with that shaft moving forward.
Who pays for that? Is that part of your program?
So that's part of our program. So that comes out of that like $15 million funding that we receive. Most of it's from the federal government through the Office of Surface Mining, Reclamation, and Enforcement, which is an agency within DOI, Department of the Interior. And so they issue annual grants to states that have mined coal in the past. Colorado, thankfully, has mined coal, I guess. So we receive funding associated with that to the tune of about 13 to 15.
So the private property owner isn't.
Nope. They're not obligated for anything, so it's at no cost to them. It's nice to be able to offer something to folks. Because a project like this, probably be $400,000. So we actually have one going on. I was there earlier today over in Lakewood, drilling and grouting a shaft over there, and that one, because of the way the mine workings are laid out, it'll probably be closer to $1 million project.
I have a question.
Sure.
I know you mentioned earlier about laws that, so really early mining, the companies weren't liable to prevent this kind of thing.
Correct.
But do you ever go after different companies, even if they left the state? Is there somebody in Colorado who's trying to get money from responsible parties?
Not really. I mean, if on an EPA, like a Superfund site, it's much easier to go after somebody. Superfund gives the federal agencies much more leeway with respect to going after companies. We don't have as much of that leeway we could. The problem is most of the companies that mine coal don't have any assets. There's no company that exists. If there was, we would probably entertain that as an option, but there's very few coal companies anymore that are solvent.
Okay, thank you.
So it's a good question, because why should taxpayers be paying for something that there might be an alternative way to recover the funds? There's just not really anybody to go after. Coal mine fires. Exciting work. So we'll talk about your coal fire projects. So kind of a picture, we don't really see the picture in the lower left very often. Most of the time, coal's not burning like that when you dig into a coal pile. Most of the time, what you see is kind of the picture in the upper left, where you just have ash pockets, and like, rarely do you have open flames. So Lewis Coal Mine Fire, so we've been working with, so this one is mostly on private property there in Lewis, or kind of Marshall area, the Lewis mine, directly adjacent to the Davidson ditch. So we had reports that the fire was more active. There's always been a kind of smoldering, most of the time dormant fire kind of in that Lewis area. We received some reports following the Marshall wildfire. I don't know, there doesn't appear to be any association, but that fire was more active following the Marshall fire. I think it's probably more a function of it's been dry. It was very dry since then, and so we noticed that soil moisture impacts how the coal fires will burn, because as the soils become drier, you get more influence, there's more airflow capacity through there, plus it dries out your vegetation on surface. So we see more influences, drier periods of time, but we had some reports that things were slightly more active. So we did a characterization, we drilled 27 boreholes out at the site, and then that's kind of a summary, I'll show you what we found, but the challenge there is we had to work kind of around the ditch, but this is really what we're seeing in this photo. There's a couple of vents, active vents there. The maximum temperatures we had at surface were about 120 degrees, which is not really coal combustion, that's like coal oxidation, which generally is not hot enough to start a fire at the surface. You've got to get up into that 400 to 500 degree range to really get a fire going. But there's concern. I mean, as you have oxygen flow, really that coal, when you've got, the way coal fires work is they're oxygen driven. So that coal can spontaneously combust as you have enough oxygen moving across it over time. And you've got insulation that allows that coal to heat up, and you get what's called thermal runaway when the coal actually starts to burn. Most of these are just oxidizing coal, where it's kind of oxidizing, it'll vent a little bit. You'll notice odors that, pretty bad odors, so it's a poor coal combustion, where the coal's not really burning, it's just kind of oxidizing, it smells really bad. That's what we were seeing here. Stress vegetation at the surface, where that coal was off-gassing the combustion, or the oxidation was off-gassing the vegetation, it kind of kills it adjacent to those areas. But what can happen in situations like this is if you were to get a collapse adjacent to where you've already got some of that coal under oxidation, and suddenly it gets a rush of oxygen, you could have a situation where you could have the coal enter combustion, and now you've got exposed combusting coal at the surface adjacent to vegetation that's dried out. So those are the kind of things we worry about, and that's why this became a priority for us, is we did see some increased activity, stress vegetation at the surface. One thing we do use a lot is snow photos on our sites. We fly a lot of our coal mine sites during the winter when we have snow cover, because it's one of the best ways to figure out where you've got surface heat, because you don't have any snow. And kind of hard to see, but this area right here is essentially that. So you can kind of depict how extensive that fire is subsurface based on heating you're seeing at the surface, and snow is a great time to take those pictures. So here's some photos, kind of the drilling. You can see the Davidson ditch through here. So what we'd identified is kind of this area right down in here we thought was probably where the coal fire was most active based on the venting, the surface melting we had seen. So we came up with a drilling program to do some kind of pattern drilling to get a sense of how extensive was the fire. So we're logging the geology underground. We install what are called thermocouples in those holes. Those thermocouples are wires that measure temperature. And so you can drill a hole, put this special wire down there, you can grout it in place, and as that wire heats up, it sends an electrical signal out. It's a special kind of piezometric wire that sends an electric signal, and you can correlate that electric signal to a temperature. And so you can monitor what's happening with the temperatures underground. You can set up a data logger, can log those temperatures over time, can see what are the trends, does weather influence the temperature of those coal fires, which it does in some cases, barometric pressure, that kind of stuff. So we did that here to get an idea how intensely was the fire burning, where did we need to do our mitigation work. And that's really the goal, is trying to define our boundary of fire. So we know, or combustion, so we know where to actually dig. These are the results of our investigation. So what we found is subsurface right here in this hole, we had a maximum temperature of about 144 degrees. Kind of located directly adjacent to the Davidson ditch, which created some challenges. But for the most part, that fire was really localized. We had ambient temperatures kind of throughout this area, and those are about 64 to 56 degrees subsurface. That's kind of what we consider ambient. So we had in the area of oxidation, kind of 144 degrees. So not super hot, but something we're at least concerned about based on what we're seeing in the surface. So we started digging it up because it's pretty shallow there. So maximum depth of coal at that location was, I think we had 30 to 35 feet was the bottom of the coal below the Davidson ditch. So you can see, here's that coal sequence right here, very evident. Obviously the black material. Most of this was kind of some collapsed debris underneath the ditch. Here's the Davidson ditch up here itself. You can see some of the steam coming out. It's not really smoke, so it's pretty wet out there. We like to do our excavation during the winter so that we don't have issues related to potential fire ignition. We're very careful when we excavate that coal to have sufficient water on site to address any issues if that were to combust suddenly. But But generally, the goal on excavation of that coal is we want to dig out the area that's hotter. So that kind of defined area, 140 degrees. What we'll do is we'll excavate the coal out, and then that overburden material, all the brown stuff you see on top, we like to spread the coal out, allow it to cool, mix it with a little bit of moisture. You don't want too much water because it actually coats the grains of coal and it causes the coal not to cool as quickly. So you add a little bit of water, you spread that material out, it cools pretty quickly, and then you mix it with that overburden material. So you try and establish a ratio of coal or carbonaceous material to non-carbonaceous material of about 10 to 1. And so when we've got that mixture pretty well, we spread it all out, mix on the overburden, mix that up, and then all that material goes back into the hillside, compacted once it's cooled. Obviously, we cooled about 90 degrees, and then that goes back into the hillside. The goal of having that 10 to 1 ratio is so we don't have contact between coal once it goes back in. So now we've got a reduced concentration of coal. So even if it were to start combusting again, it doesn't have contact with adjacent grains to continue to combust for a very long period of time. So that's the best way we've found to extinguish coal mine fires. You always put extinguish in quotes because it's difficult to fully extinguish a coal mine fire, because if there's coal, there's always a possibility of those grains oxidizing over time. But in a situation like this, we're pretty confident that we've addressed the fire.
So when you say there's a 1 to 10 ratio, you're talking about 1 being the coal and 10 being the overburden?
Correct. Yep. So you're diluting that coal in your backfill material. So that's when it's nice that we have a bunch of overburden material that we can mix. The more you mix in there, the more diluted that coal is and reduces the potential for future ignition. So it was directly adjacent to the ditch, so we had to carefully excavate right up to where the ditch was because we couldn't remove the ditch. And so here's kind of the final product. So you'll see this was some of those pictures before where our project manager was standing. That's kind of right in this area. So it's all been recontoured to kind of what the original surface grade would have looked like, and then revegetated, planted some trees down below there. So we maintained a couple of those temperature monitoring equipment so that we'll have an idea as to whether or not we've fully extinguished the coal. We were able to, I think we had a snowfall not too long after we completed the work. So we did take some pictures and we didn't have any melting on the surface there, but we'll come back the next few years, check surface temperatures to see if we've been able to fully extinguish it. But I think based on what we were able to excavate, we feel like pretty confident this one's been extinguished.
So is this, this isn't Marshall Mesa?
No.
It is?
No.
Oh, okay.
So this would be Cherryvale, Marshall Road. It's to the northeast of Cherryvale and Marshall. So I probably should have put that up there. Just assumed everybody would know, but I'm sorry. So if you're coming down Marshall Road, it's that residence. There's a couple of residences to the right there as you're headed to the west on Marshall Road, right before you get to Cherryvale. So it's kind of up on the hill there. It's Boulder County open space on the north side, but it's all private property on the south side of the Davidson Ditch. So, and then it's where they used to report smoke sometimes coming out of the ground in that area. So.
Is what you're doing sort of cutting edge, the newest stuff, or are people doing this all over the world with coal mine? Is it a little new that people?
I think it's a little new about trying to excavate, and I think in the past we would have tried to do non-invasive means because it's really expensive to dig. And this project actually came in pretty inexpensive. I think it ended up being overall about $600,000 to $700,000 when you include the investigation. So not crazy expensive to fully extinguish it. In the past, a lot of times what you do is try and do injection. So you might drill a bunch of holes, try and inject grout in the ground to take up space and put out the fire. You don't typically inject water because what happens is you'll get steam explosions. So you build up steam pressure and explodes. So never try and do direct water injection. So you're doing some kind of a grout. Grouting is difficult because it kind of pushes the fire around, but you never fully extinguish it. Even when you can extinguish something, a lot of times what you have happen is that adjacent rock becomes so heated over time that it takes a long time for that adjacent rock to cool, that even if you put out the area that's burning coal, there's enough latent heat remaining to heat that coal back up once you have left the site 2 years later, because it just retains that heat. That's why being able to fully excavate something, spread it out, dilute it, and then put it back in there is the best way. So I don't know that it's cutting edge because people dig up things all the time, but I think we've been able to demonstrate success in Colorado doing that on a couple of different fires. This being one of them. So, yeah. Marshall, that's for last. So we're in the mitigation phase now. We'll be beginning mitigation in about 3 weeks, I think. Our contractor was out there the other day doing some initial staking. They're moving some trails around associated with the trailhead there. But this is kind of a snowmelt picture from, this is 2002 or 2022. But you can see this area here's the lower, that would be the northeast parking area. Snow's completely gone in that area. And then as you move towards the south, so this is 93, so that's towards the south of the trailhead, is another area where we're seeing some snow melt. So obviously this is a priority underground mine fire for us, just based on proximity to infrastructure, much like Lewis is. And then when you're seeing surface impacts like that, where you know you've got subsurface heating that's melting snow, priority site. This one's pretty shallow, much like the Lewis. Maximum depths, I'll show those in a minute here, but for the most part, it's in the 20 to kind of 35 to 40 foot range. So it's pretty accessible. When you're asking about excavation, we can really only use it where we can actually, I think the deepest excavation and cooling that we've done is about 100 foot. And that's over, it's what's called a Wise Hill coal mine fire just outside of Craig. So we were able to excavate down 100 feet there to capture the coal mine fire. And that's pretty much the maximum depth. You start getting above 100 feet and the excavations just become extremely expensive and difficult to manage.
So I have lost my bearings. What's the road and where are we?
Okay. So this is 93 right here.
Okay.
That's south on 93. This is where Marshall
Oh,
Road
I know where that
connects.
is.
So that's the stoplight right there.
End of Marshall Road
Yes.
at 93.
Yep.
Okay.
Sorry.
And that's that little store and gas.
Yes. Yeah.
Keep those.
Yep.
Do that curve.
So yeah, all that's to the west side of, or the east side of 93. Right there, Marshall Mesa Trailhead. So mitigation work, like I said, is starting in a couple of weeks.
So is the Marshall
That's
Mesa
super.
trailhead, is that all to be closed for?
Yes, the trailhead's gonna be closed. Yeah, I know. I'm sorry. We're trying to do it as expeditiously as possible. I believe we've been able to work with the city to at least maintain trail access across there. There's gonna be temporary trail access on the west side of the trailhead parking area that you can get around the construction area, but you're not gonna be able to park there. So, but the city, so our work will hopefully be done by, start now, we're hoping to have it done by January, February. But then the city is gonna follow on after our work to do a reconstruction of the parking area. So it will be closed longer based on their work. Not to blame them, but we're actually partnering with them to do our work and then do some grading so that they can come in and do their final reconstruction of the parking area. So here's some just examples of our investigation work there at Marshall. This site we drilled a lot of holes, trying to really characterize it. Couple of interesting things on this slide. So here you can see all the blacks. That's typically what we're seeing when we intercept the coal sequence underground, and very definable visual evidence of where you hit coal, where you don't. Interestingly, you'll hit these areas of red in there, and it's not really sandstone. Some areas it's sandstone, but that's where the coal's already burned. So that's ash zones. So you can begin to define where there's no coal remaining because it's already burned, or where you actually have coal is still unburned, so there's the potential for combustion. So you can start to get a pretty good geologic picture of what's going on underneath there based on having a number of holes drilled. So as part of that investigation, we drilled 67 borings over that area, stretching all the way from here, the Davidson Ditch where it goes over Marshall or underneath Marshall Road, all the way to the north up to pretty much the intersection here with, in the town where Marshall Road takes the turn there. So borings all across here. We also did some test pits, because sometimes just drilling a hole doesn't give you as much of an idea. You get a pretty good picture of geology, but actually digging that test pit with an excavator bucket gives you a really good idea. You can identify the sequences where there's any kind of confusion. So we did some test pits in addition to the borings. And then we did a lot of those thermocouple installations, kind of all across the site to get an idea where we had higher temperatures and then how things change with weather. Maximum temperature we observed was 241 degrees, and I'll show you kind of a picture where that is, but it's over here in the parking area at depth. So hotter than the Lewis by 100 degrees.
So where was the main shaft for that? Because this would be room and
These were room and pillar. So the dip of the beds is towards the kind of southeast. Most of these are slope entries right here because it's pretty shallow. So they actually sloped in. We don't have good maps for Marshall number 1, which is this area here. This is Marshall number 1. Marshall number 3 is back over in here, and it looks like, based on the map, there was a slope entry that came in this direction through here. So actually starting on the west side of 93, but we haven't really found good evidence of where that slope entry is on the west side. So it's kind of difficult. There may have been another slope entry kind of somewhere in here, we think. But there's no shafts kind of in this area this way, no shafts. The first shaft we see is down over in here. There's a shaft, there's a coal waste pile directly adjacent to one of these trails. You've probably walked by it. That's the shaft on maybe Marshall 5 or 7. There's like 7 or 8 different Marshall lines kind of within that Marshall basin there.
But when did they all stop operating? You know?
I believe those were a little bit earlier because those were some of the first mines in the district because that coal outcrop there, so it was easy to access. Depths were shallow, so those started, kind of late 1800s. I think most of those petered out, certainly down in the lower section, more like in the 20s. There may have been some mining in that Marshall area into the 30s. Up on the hill above the Davidson Ditch, right below where the Marshall Reservoir is, I think there's Marshall number 6 and 7. I think those were later mines, kind of in that area, a little bit bigger. But the area right there in Marshall was some of the oldest mines in the.
Yeah, on the side of the
Yeah,
hill.
mine means that's on the rich side.
Oh, did it?
So you can check and see if I remembered correctly or not.
So up on the hill is where it smoldered for years and years and years, right?
Most of the smoldering is kind of in this area down here, we think.
Now or past?
Past and now.
Oh, okay.
So like the historic pictures they had in their kiosk down here. I don't know if you noticed those at the trailhead. There's some old historic pictures they had in the kiosk. I think those pictures were kind of from this area over here. And Lewis also.
So that white area on the right, down the little white,
Oh,
is that those limestone slabs on the trail?
I don't think so. I think those are farther this direction because I don't think you hit the limestone yet. I think this is, I can't remember. I think that's an area of just eroded sandstone over there. But I've hiked the trail a few times, but not probably as many times as you have. So if that's what you're thinking is the limestone, I'll defer to you. But
It's just like this area that suddenly, the trail turns suddenly into like this limestone, like the size of this road.
I think it's actually farther, but but you do get some sandstone outcrops kind of along here, which are over the coal. And then this obviously dips down. You kind of got this ridge that runs right through here. And then this dips to the east. The topography and the coal dip to the east as you move that direction.
And then there were rail lines there too, right? The old rail bed.
I know rail came into the old town marshal, and then I think they had some spurs that came down to a couple of the lines right off of the main Marshall Road. But I think the Marshall Road is essentially the rail line. Pretty sure. So this is a nice colorful picture of depth to bottom of coal or rubble. So you can really see the lighter colors, that's kind of 10 to 20 feet. So that's most of this area through here is about 10 to 20 foot depth. As you move, like I said, towards the east, kind of southeast, you start getting into the blue is 45 to 65 feet. So that's the maximum depth. We didn't really go a whole lot farther to the east than that. We don't see any evidence of heating. And at some point, you're not going to dig up the entire open space. So it doesn't do us a whole lot of good to dig out there because really focused on that area that's shallowest and where we know we've seen surface heating. But the coal does continue that direction, just at much greater depth. Another photo, this, I kind of mentioned before how you can document where the coal's intact when you see the black coming out of the hole, or you've got the red and ash color indicating a burned area. So the green is where we're actually below the coal seam, so it's already been eroded off, so there's no coal along that section there. It's missing, so it's been eroded, most likely. The yellow is where we're actually seeing burned or rubbleized coal, so it's already burned or it's collapsed. And then where we're actually seeing burning, it's smoldering more than anything, or ash zones are kind of in the orange. And then we've got some intact coal kind of right through this zone in here that's still remaining unburned. So the areas that are a priority for us when it comes to excavation are going to be the areas that are currently burning or smoldering, and then areas that are unburned coal that could potentially burn in the future. Since we're already there digging out the burning coal, extending the excavation farther to the north to address areas that have unburned coal, it's easy enough at that point. And then that just reduces that future risk of combustion.
So the road won't be closed when you're doing this. But
Yeah, so we'll be able to, so this black line is kind of indicating our area of construction. I've got a better picture in a minute that shows, but really that's our area of investigation. Really our area of construction is going to be kind of from here up to this area, but we're going to always be to the east of the main road. So none of this will be closed on the road, it's just the parking area will be closed and that trailhead. So here's our kind of temperature areas that we've outlined, where we had something above ambient. Like I mentioned before, this area here is our hottest, kind of pushing 240 degrees. And hopefully you can kind of see, here's those parking areas. So here's the kind of eastern parking area. Here's that kind of northeastern parking area. So it's really focused right on that northeastern parking area. We have burning underneath the parking area, which is why we actually had the kind of county open space closed that parking area a couple of years ago when we identified that, because we knew we had burning pretty close to the surface right there. This area up here was a little bit warmer, not significant, but that is where we have some of that unburned coal. So we think that might be pre-oxidation that's occurring in the coal. So we want to go ahead and dig that up, remove that potential. And then to the south of the trailhead down here is kind of where the other area of smoldering coal is that we want to excavate. So here's our excavation mitigation design plan. So we have really two areas of excavation. We have a south area, which is kind of that area south of the parking area. And then we have kind of our northern excavation, which will extend from kind of both of those parking areas currently up to the north and east, where we know we have some unburned coal, where there may be some pre-oxidation occurring. But it's going to be pretty limited to this area here. It'll be progressive, so we'll dig a little bit, mix some of that coal, put it back in, move to the north, dig coal, mix it, put it back in. So it'll be kind of a progressive excavation where you're not going to have a huge pit open at any one time, because we have some restrictions on, as we dig that coal, we cannot have any coal over 80 degrees exposed at surface overnight, because we don't want to have any kind of potential for wildfire ignition, anything along those lines. So any coal that we excavate during that day that's hot will get cooled, mixed, and put back in place. So none of it's left unattended. So anytime we have hot coal, which we're defining as above 80 degrees on surface. We'll have people on site to be cooling the coal and then to placing that back in. And then anywhere in our excavation that exposes hot coal, we'll be putting material back on that excavation so that we don't have any hot coal exposed during the process. So trying to work progressively so we never have too much exposed at any one time, and then trying to keep that excavation reasonable. It's going to be unsightly initially, but trying to keep that as relatively small as we can while still trying to move through that area as quickly as possible. So it'll end up being about 182,000 yards in total over the course of excavation. Like I mentioned, the depth will be about 30 feet. It may go deeper in a couple of spots depending on the topography. And it'll be final graded. There'll be some revegetation, but as I mentioned, the city's coming in following our work to construct a new trailhead, parking area, et cetera. So we're gonna grade it for them kind of as a courtesy. So whatever they're within 6 inches of what they want for their final grade. And then areas that are not gonna be part of the parking area construction, we'll do some re-veg on, recognizing those will be areas that won't be touched again. So that's the plan that we have moving forward,
And that's starting this month,
starting this month.
like tomorrow.
No, we worked out a deal with the county. So the county, or the city wanted to make sure that their high school mountain bike teams could still access the trailhead area. We were gonna start October 1st, their season, my kid used to race, so I know, their season goes until mid-October, so we okay, fine, we can wait until roughly November to fully close that kind of area there. So it'll be starting, I think the third week we'll be mobilizing some equipment out to the site, but not really starting excavation in full until that first week in November. You'll see equipment, but it won't be doing anything until November most likely. But and we're hoping, based on conversations with the contractor, that he's got a pretty aggressive plan to move through the excavation. I'll have some really big equipment there, which would be interesting in that small area. But we think January, February should be done. It might be done earlier than that. We're
And
really
the weather
trying.
doesn't affect you?
What was that?
The weather doesn't affect you?
Not generally, actually, it's to our benefit. We much prefer it to be cold, snowy. It makes it easier to cool the coal. And we don't have any kind of risk of wildfire ignition, and just all those things work in our favor. The challenge with working in the wintertime is just your period of daylight is small, so you don't get as much benefit from being out there on a daily basis. And it takes a little longer to get the equipment cranked up in the morning before it can get going. But so it does have an impact, but the trade-off with respect to having cooler temperatures and snow on the ground is to our benefit. So, there may be a day or two where we can't work if it's really heavy snow or something. So I think that's all I've got.
I'm just wondering, how many other areas in the state are you actively working to mitigate, or are there any others right now?
So there are. So I mentioned kind of like Grand Hogback is where we have some very active coal mine fires. We're seeing temperatures there where we have 1,000 degrees on surface. So almost an order of magnitude higher temperatures. So there's a couple of fires. It wouldn't mean anything to you, but IHI is a fire just north of Rifle. Headed up to Rifle Falls, so we're working on that one. South Canyon, which is directly adjacent to Glenwood Springs, which we believe was a location where the coal seam fire started in 2002 or 4 that burned some homes there in Glenwood Springs. So that fire is extremely active. It's burning on both sides of the valley, very steep topography. We've had a couple of ongoing projects there, and we're doing some investigation work this year. It's another fire over near Paonia that started a wildfire 2 years ago. So it was a 5-acre wildfire that started on an outcrop that's burning. That fire, we've done some drilling. We're getting ready to do some design. The challenges on most of those fires, kind of on the west slope, either in the Grand Hogback or towards Paonia, is that topography doesn't lend itself well to mitigation. Here, one reason why we're focusing on Lewis and Marshall outside of just the location in terms of infrastructure, the topography is really conducive to excavation and quenching. So they're fires that may not be burning as intensely as some of our other high priority fires, but we can actually put them out. So we can dig them up, put them out, check them off the list. So those are kind of priority areas for us, but we've, at any one time, we're monitoring, our highest priority fires is probably 12 to 15 that are really high priority based on temperature and activity. And then we do every 5 years, we go through and monitor all of the fires in Colorado, whether they're dormant or active, and do a kind of inventory of those.
So you've mentioned that the winter temperatures are more conducive to what's the word? Not ameliorating.
That's mitigation, yeah.
Senior moment there. To mitigating this problem, and obviously the Marshall Fire happened at the end of December. It wasn't that cold,
Right.
but it's colder than, say, July. So, and there was such huge wind, and there are all these factors that
Right.
added to it. I mean, has any, I know that you're sort of putting the blame on several different aspects of the environment that day. But is there any way of sort of explaining further the fact that it happened in the middle of the winter?
I mean, we've done obviously some investigation work. We shared all of our findings with the sheriff in terms of trying to determine, fire start, location, all that kind of stuff. I can't really speak to what happened on that day. I just know that the fire itself, what we're seeing from an underground mine fire standpoint, is we don't see extremely hot temperatures. With respect to conditions, like and how that might influence our excavation, if you were to have similar conditions like we had during the wildfire ignition at Marshall. Like I said, we put some restrictions on having hot coal at the surface. We're also not working when we have high wind days, so anytime we have the potential for a high wind day, we're not gonna work. So we will have to work around some of those wintertime conditions if it's similar to what happened back in December of 21, but for the most part, I think we've at least addressed the potential for that in our work. With respect to what happened at the fire ignition, hard for me to connect any dots with respect to the mine fire. I know they didn't find that there was initially any kind of correlation between the two, and based on the fire activity we've seen, and then some monitoring we've done since then with respect to weather patterns and fire, we haven't seen weather influence the temperatures at the fire over the last 3 years since we installed those thermocouple wires. So it doesn't appear like there's as much weather influence on that fire itself. So hard to speculate. I hate to speculate too much. So.
Well, Jeff, thank you so very much. That was just terrific, and maybe we have time for one or two questions before we grab a cookie and go home.
So does your group also deal with, abandoned oil wells and all of that is another whole?
It's another group within DNR, so they're part of the Energy Carbon Management Commission. It used to be OGC, but they have an orphan well program that does methane or caps those abandoned wells. Not being abandoned wells.
Well, there was a lot of information in this program that, ladies and gentlemen, so hopefully found to your benefit. And once again, Jeff, thank you so much.
You're welcome. Don't be
Still some cookies over on the table. And,